There's something new that happens with accelerations when we go from motion along a line to two-dimensional motion. And I'm going to, in other lecture videos, I talk about how to calculate that. But in this one, I just want to talk about your intuition. If you look at something happening, how do you have a sense of what the direction of the acceleration is? So acceleration is always, whether you're in 1 dimension, 2 dimensions, 3 dimension. Acceleration calculates, tells you how quickly the velocity is changing. And if the velocity is not changing, if you have constant velocity, then there's zero acceleration, and that's always true. But if you have motion along a line, acceleration can only mean one thing. It can only mean that the speed is changing. So an object can only be speeding up or slowing down. But since velocity has a direction, when you get into 2 dimensions and 3 dimensions, you can have the velocity changing even if the speed is not changing. It's a hard thing to get used to. So in 2-dimensional motion, it can mean either one or both of these things. It can mean that the speed is changing. And or it can mean that the object is turning. Okay, that's something that's not available if you're moving along a line. There's no such thing as turning. And so to visualize the direction of acceleration in 2D is a little tricky without some sort of new tools. And so here is, I'm going to give you sort of an approach to thinking about the direction of an acceleration. So in order to visualize the acceleration vector, and we're only going to be talking about the direction of the acceleration vector here. But still, this is something that's very useful, I think. So the first thing you want to do is draw the object's path. The path that the object is following in space. The second thing you want to do is draw the velocity vector. Everything is going to be based on, comparisons to the velocity vector. And the velocity vector at any point you choose along the path is going to be tangent to the path in the direction of motion. I'll do examples when I'm done with this. So second, we're going to draw the velocity vector. And it's going to be tangent to the path in the direction of motion. Now, the velocity is not an acceleration, so that doesn't tell us anything about the acceleration, but we're going to use that to base the next things on. So the third step is if the object's speed is changing, then there's two possibilities. It can be speeding up. In other words, the speed is increasing. And if it's speeding up, then draw a part of the acceleration that's parallel to the velocity. I'm going to call it A parallel, like this. If it's speeding up, it's going to be in the same direction as the velocity vector. This isn't too much of a surprise because we've already talked about the fact that if an object that's moving along a line is speeding up, the velocity and acceleration are in the same direction. And if it's slowing down, they're in the opposite direction. So then you can, I'm sure, guess what I'm going to say about an object if it's slowing down. Then you're going to draw that parallel part of the acceleration, the part that's parallel to the velocity, in the opposite direction of the velocity. And then the fourth step is if the object is turning, we're going to draw a part of the acceleration perpendicular to the velocity in the direction that it's turning. So I'm going to call this A perpendicular. It's a part of the acceleration. And remember, it has to be perpendicular to the velocity. That's why I give it this name, A perpendicular. So it should always be 90 degrees from your velocity vector, one way or the other. Yeah, in direction, actually, let me write this different. In a direction, sorry about that. Draw a perpendicular in the direction that the object is turning. And then the last thing is the total acceleration is just the sum of these two parts. So if there's only one of these two, then the total acceleration is in the direction of that. If both of them are there, the total acceleration can be in any direction between these two. So if both of these two parts are non-zero, then the direction of the total acceleration A is between these two, between the directions of A parallel and A perpendicular. Okay, so let's see some examples. The first one is the case where this is moving along a line. You have a ball that's rolling down a ramp, and let's say, gravity is making this speed up as it rolls down the ramp. And so the path of this motion is this. I'm going to put the motion right through the center of the object. Okay? Well, it's moving down the ramp, so the velocity vector I'm going to draw in the direction of motion, and that's this way. Okay, so that's that's velocity. Okay. And now it says that it's speeding up as it goes down the ramp. Speeding up, if you look at number 3 here, says that A parallel is in the same direction as the velocity vector. So this green is my A parallel in the same direction as V. And now we have to think about whether it's turning. This is moving along a straight line, so it's not turning. And so the answer is, for the total acceleration is equal always to the sum of the two parts, but this one is 0. And so this total acceleration we know is in that direction down the ramp. Okay? So this is an example where it's changing speed, but it's not turning. Now let's think about an opposite case where it's not changing speed, but it is turning. Like imagine something spinning around a circular, moving around a circular path with a constant speed. So in this case, the object has a constant speed as it travels around a circular path. Okay, well, let's say that this is the path of the object, and let's say we're thinking about the acceleration of the object right there. Okay, and let's say that it's going around this way. Okay, the velocity vector is tangent to the path in the direction of motion, so there's the velocity vector. It's not changing speed, so there's no parallel part of the acceleration. And so the last step is it turning? Think about kind of which way you'd have to turn the steering wheel to stay along this path. If you didn't steer at all, you'd keep going along the velocity vector. But in order to stay along this path, we have to turn the steering wheel this way. And remember, those two have to be 90 degrees from each other. So this is your A perpendicular. Well, as always, the total acceleration is the sum of the two parts of the acceleration. This time, this one is 0. And so the total acceleration is toward the center of the circle like this. Okay, for the last example, we'll do one where we have both of these two things. So let's say this time the ball slows down as it rolls up this curved ramp. This time the ramp is curved, so it's not moving along a line. And so there's the ramp. Okay, how many am I going to draw? Let's just stick with this one. Okay, so it's rolling up this curved ramp. So first let's draw the path of the ball. Okay, so there's the path of the ball. It's rolling up the ramp. And so the velocity vector is tangent to the path in the direction of motion. It's slowing down. And so if it's slowing down, A parallel has to be opposite of the velocity vector. So there's A parallel. Next, it's moving from lower to higher along this ramp. So which way do you have to turn the steering wheel to get this to stay along the path instead of continuing along the velocity? The answer is you have to turn the steering wheel this way. So here's your A perpendicular. And this time, since we have both of these two parts, the total acceleration, we can't say for sure what its direction is from this kind of analysis, but we can say that it's somewhere in this range of 90 degrees. So the total acceleration is somewhere between A parallel and A perpendicular.